So again, I welcome you for the series of chemical equipment design. We are going to discuss the scale up of the agitation vessels. That is, the scale up means in actual laboratory, we are doing certain experiments, and those experiments they are carried out in the small vessels of say 500 ml beaker or the round bottom flask or conical flask or say 1 liter or at the most 2 liters capacity is used in the laboratories in general case. Now all this 2 liter capacity or 1 liter capacity has to be used for say the 2000 liters or say 20,000 liters or 10,000 liters capacity production. That is what is the industrial scale production, actual scale production from a model which is in the laboratory. Sometimes it has to be brought to the pilot scale. Now what is the pilot scale is in between the laboratory scale and the actual full scale. Actual full scale, that means actual unit of production manufacturing in the industries. So in between that, whether I am getting the same results as what I have got in the laboratory, are the same results are obtained in the pilot scale, that is first to be checked. So I will first check my results with the pilot size reactor. First I will do in the laboratory, then I will increase its volume and will try to do it in the pilot scale. If I get the proper results in the pilot scale, then I am going to enlarge that vessel to the production, actual production stage. So this is the any development that is in these three steps, that is laboratory scale, pilot scale and the full scale or industrial scale. Sometimes this pilot scale that is eliminated, that again depends on the type of a product. So what is to be done to enlarge or to scale up from the laboratory to the pilot scale or to the full scale? So what is the scale up procedure that we will understand it? Calculate the scale up ratio. First thing is to calculate a scale up ratio R. Assuming that the original vessel is a standard cylinder, that means a cylindrical vessel we are considering. We are considering a beaker in the laboratory. We are not considering a round bottom flask. We are considering a laboratory. Because our general vessels, there are cylindrical vessels we are considering. Round bottom flask, that is a spherical vessel. So in our actual industrial production, it's a cylindrical vessels they are used. So generally the considerations are from the point of view of a beaker. So what will be the volume? And another second consideration is the diameter and the height. They are taken as the equal. Height means the liquid available into the beaker, the height up to which the liquid that is available in the beaker, that is the liquid height. H1 is the liquid height, dt1 is the tank diameter. So this is our first assumption, that is the tank diameter is same as the liquid height. That is assuming the original vessel is a standard cylinder and the tank diameter which is equal to the liquid height. So volume which is equal to pi by 4 into d square into the h. But as dt1 which is equal to h1, so this equation simplifies to pi by 4 into dt1 cube. The ratio of the volume This V1 is the volume for the laboratory scale and V2 is the volume for the actual scale or the full scale or the prototype or the production type. So I can similarly write as pi dt2 square upon 4 and V1 as pi dt1 square upon 4 into the H1. So which is equal to the dt1 cube upon dt2 cube upon dt1 cube. After simplification of this, you will get this thing. So the scale up ratio, that will be R, which is nothing but the diameter of the tank 2 to the diameter of the tank 1, which is equal to the volume of the tank 2 upon volume of the tank 1 raised to the 1/3. So because it is coming as the d cube, so it's a scale up ratio. So first thing is to calculate a scale up ratio, that is by using the V2 upon V1 raised to 1/3, which is nothing but the diameter of the tank 2 upon diameter of the tank 1 ratio. Using this value of R, apply it to all the dimensions of the original vessel. That means original vessel is the laboratory scale. To calculate the new dimensions of large scale or the prototype or the production scale. So dA2, which is equal to RdA1. For generalization, J2, which is equal to RJ1. That is what we can generalize it. Then determine the agitator speed N2 to be used to duplicate the small scale resulting using N1. So it's a speed ratio that is taken into account. N2 upon N1, which is 1 upon R raised to the N, which is nothing but N1 into dt1 upon dt2, where N, which is equal to 1, for equal liquid motion, N, which is equal to the 3/4, for equal suspension solids, and N, which is equal to 2/3, for equal rate of the mass transfer, that again varies depending on the type of the fluid and may vary. And next thing is to know the N2, that is the speed of rotation. The power required can be determined by using this power number Np, which is P upon rho n cube dA raised to 5. And then finally use this graph, that is this graph will vary from fluid to fluid, from impellers, for it will vary for different liquids. So every liquid, every vessel will have the different graph. Now this is the two considerations. Two kinds of conditions must satisfy to ensure the similarity between the model and the prototype. That is, first is a geometrical similarity of a physical boundary, and second, the dynamic similarity of a flow field. There are two similarities for a scale-up process. One is geometric similarity, that is related to the physical boundaries, and second, the dynamic similarity for the flow fields, that is the fluid motion dynamic, which is in motion. And first is the geometric similarity. So this geometric similarity of a physical boundary, the same type of a reactor, that is the first condition. All linear dimensions of model must be related to the corresponding dimensions of a prototype by a constant scale-up factor R. So मॉडल के जो कुछ डायमेंशंस हैं वो अपन करस्पॉन्ड कर रहे हैं प्रोटोटाइप डायमेंशंस. Then keep the ratio of height h to the tank diameter dt same in the model and prototype. Now this is the second case we will consider. First case we have considered as H upon dt, which is equal to 1. Now we are considering H upon dt, which is 2. So consider the example. For example, 2-liter vessel is scaled up to the 2000-liter fermenter by geometrical similarity, where H upon dt, which is equal to the 2, that means H equals to 2 times the tank diameter. H is equal to the 2 times the tank diameter. Then impeller diameter is given as 3.24 centimeters. What are the dimensions of the model? That is, what is the height, what is the tank diameter, and what are the dimensions of prototype. So we know the volume, we know the height to diameter ratio, and we know the impeller diameter. From there, we have to design a prototype. So volume is pi by 4 d square into h, where h is in this case is 2 times the tank diameter. So v, that will be equal to pi by 2 dt cube for model. So simplifying, substituting the volume Vm as 2, you get dTm, which is equal to 10.8 centimeter. So you can calculate the Hm, that is 2 times the dTm, which is 21.6 centimeter. Similarly, volume of a prototype now, that is pi by 2 into dTp. This is coming as now P for a prototype. And we are knowing the scale up ratio as dTp upon dTm, that is dt2 upon dt1, which is nothing but the diameter of the tank in the production scale upon diameter of tank in the laboratory scale. That is nothing but the volume ratio, which is 1/3. So in this case, it comes out as the 10. So similarly, dTp, diameter of the tank in a prototype, will be 10 times the diameter of the tank in a model. Similarly, height in the prototype will be is equal to 10 times the height in the model. It comes out as the 216 centimeter. So h upon p, hp upon dp, which is equal to 2. This is one simple example showing the geometric similarity. Now coming to understand the dynamic similarity of the flow of the fluids. To understand this dynamic similarity in a stir tank, the use of a dimensionless numbers that is needed. That is, what is the power number, Reynolds number, and Froude number. Power number PO, which is rho n cube di raised to the 5. Reynolds number rho n di square upon mu, and Froude number Fr, which is equal to n square di upon g, where PO energy input in power and impeller speed, that is RPM, rho density kgs per meter cube, di impeller diameter, which is 30 to 40% of the diameter of the tank dt, then mu viscosity, acceleration due to gravity. However, it is difficult to satisfy the dynamic similarity when more than one dimensionless group is involved in a system. This is very important. It is very difficult to satisfy the dynamic similarity when more than one dimensionless groups they are involved. Here 3 dimensionless groups are involved. That is power number, Froude number, and Reynolds number. So 3 dimensionless groups are used here. So it is very difficult. So we have to restrict it to the certain limitations. So designing criteria related to the dynamic properties in a stir tank system, that is the for constant power, that is P upon V, or the constant liquid circulation rate. that is Q upon V. Then constant impeller tip speed, that is N into di. N into di is nothing but the velocity, constant impeller tip speed. Then constant Reynolds number, that is N rho N di square upon mu. Now to the scale up. So your power number, which is in proportional to the n cube into d raised to the power 5, volume is directly proportional to the di cube, and volumetric flow rate, that is the n into di cube. So designing the constant power input, which is P upon V ratio, which comes as the P n cube di raised to 5 upon di cube, and after simplification you will get n cube di square. Then Q upon V, which is nothing but the n di cube upon d cube, which is equal to the n. The constant impeller tip speed n into di, and constant Reynolds number, which is equal to the Re, is directly proportional to the n into di square. So since dt is proportional to the dt, the above relationship is also valid for the dt. So in the scale up of a stirred tank reactor, the design calculations are as follows. Determine the scale up factor, that is dp upon dm, diameter of the prototype to the diameter of the model. Then calculate the dimensions of the prototype. Then select the criteria for selection of dynamic properties. That is what we are doing it. So we will consider the example associated with the dynamic properties. So the same problem, numerical, that is 2-liter vessel scaled up to the 2000-liter prototype, h upon dt, which is equal to 2 times, diameter of the impeller is same 3.24. However, the impeller speed is 500 rpm. In this, the added thing is the impeller speed, that is the 500 rpm. What is the impeller speed of a large reactor? So scale up ratio already we have calculated as the 10. The diameter of the impeller, that is calculated as the 32.4 as in the above case. Now coming to the for constant impeller tip speed, n into di, n for the model, speed of rotation in the model, the tank diameter for the model, which is equal to the speed of rotation for the prototype and the tank diameter in the prototype. This ratio is for the constant impeller tip speed. So you are knowing the 500 rpm, that is the speed, and diameter of the impeller, that is coming as 10.8, and dtp, which is 108. So this 50 rpm, that is the ratio. So 500 rpm is required for a model, and when you are choosing it for a prototype, its speed, that is reduced to the 50 rpm. That again varies on the ratio R. The constant Reynolds number R is directly proportional to n into dt square. So n into dt square for the model, n into dt square for the prototype. Compare that, you will get the n as 5. So when you consider the tip speed, impeller tip speed as the constant, you get the 50 rpm. When you calculate from the perspective of a constant Reynolds number, you get it as the 5 rpm. So what is our statement? That is, it is difficult to determine so in scale up, generally any of the above criteria should be met with the geometric similarity boundaries. However, it is difficult to satisfy the dynamic similarity when more than one dimensionless groups are involved. So we have considered the two different factors, that is the speed and the Reynolds number. impeller tip speed, you get 500 rpm, 50 rpm, and for constant Reynolds number, you get a 5 rpm. So this statement holds true. It is difficult to satisfy the dynamic similarity when more than one dimensionless groups are involved. So it is to be calculated based on single consideration. In scale-up, generally any of the above criteria should be met with the geometric similarities. So either we have to think of the constant impeller tip speed or the constant Reynolds number and do the further calculations. So either consider this and use this impeller tip speed criteria, or consider the constant Reynolds number and consider this as the rotational speed.